Hello and welcome to another lecture for my class, PSYC 440/640, the class that's called Experimental Methods, but is really more of a class on univariate data analytic techniques from a model comparisons perspective. And once again, a webcomic from phdcomics.com. Some humor there, which I think needs little explanation, at least to those of us who've been through or are currently in graduate school. Anyway, today's lecture is called More About ANOVA, Coding and Contrasts. It's basically just that. I'm going to continue talking about coding, dummy codes, contrast codes, and a few other important issues related to ANOVA. Now, before we get there, though, let's briefly revisit that little exercise or activity I asked you to do last time. I wanted you to find a study in your area of interest and read it carefully, especially read the results section carefully. The reason I wanted you to do this is because I want you to focus on the way the research is presented, the way the analyses particularly are presented. Is the research presented as exploratory or confirmatory research? Is it clear from how the authors introduce the analyses that they're going to be doing? Are the hypotheses that they make clear, or are they vague? Can you guess how many tests will be needed to fully evaluate each of those hypotheses? If you can guess how many tests you'll need, how many constitute that family, well, how big are the families of tests needed to evaluate the different hypotheses in your area of, in the paper that you're reading? And what's the family-wise type 1 error rate for each of those families? And finally, what do the researchers do, if anything, to control for family-wise type 1 error rate? As I said last time, I think in a perfect world it would be clear when you read a paper or skim a poster or talk to a colleague about their research. It should be clear the type of research that's being done, the nature of the hypotheses, the number of tests needed to evaluate each hypothesis, and also any efforts that have been made to control the problem of family-wise error rate. Now, of course, we don't live in that perfect world, and so a lot of the times what you get in a results section of a paper is a sort of a vague kind of almost story about how the analyses were done, and you sometimes wonder if important bits were left out, particularly information about how many tests were done before the final tests that are being reported in the paper, and what, if anything, was done to control for the potentially serious problem of family-wise type 1 error. Anyway, this was just a little example or a little activity for you to do, but hopefully it gets you thinking, and you can do this in the future when you read other papers, and certainly when you write your own result sections for your own research. Okay, with that out of the way, let's talk a little bit about what we're going to do today, or what I'm going to try and cover. I'm going to present ANOVA as regression again, talking about interpreting coefficients from dummy coding. I'm going to talk about different ways to do ANOVA, and I'm going to talk about contrast coding, that is, doing coding in a way that is not dummy coding, but is similar, but gives us a slightly different take on partitioning variance for contrasts. Okay, so last time I introduced dummy coding. This is a way of representing or coding a categorical predictor variable that has more than 2 levels, and it's accomplished by creating sets of dichotomous predictor variables which have specific values. In the case of dummy coding, those values can only be 0 or 1, and dummy coding works by assigning all 0 codes, so 0, 0, 0, 0, 0, however many dummy code variables you have, to the level or group of the predictor variable that is the most reasonable comparison group or kind of baseline group or control group. In the case of a drug study like the example we've been using, it makes sense that the placebo dose group would be given the 0, 0 codes, because that's the group we're probably going to want to compare back to. We're going to compare the low dose to the placebo, the high dose to the placebo, and so having 0, 0 for our placebo dose group makes sense. Then the other groups, the other levels of the predictor variable, get other combinations of 0 or 1, and they can be any combination provided that they are unique. You can't have the same code for 2 or more levels of your predictor variable. So the low dose group and the high dose group in this example have to have distinct codes. Once you've done that, you're set. You have now dummy coded, you've represented the levels of your categorical predictor variable using a set of dichotomous predictor variables that can only have values of 0 or 1. Now, you've done this, and you may be wondering, well, what do the coefficients in my regression output mean? I enter these dummy-coded variables into a regression, I get an ANOVA table, which gives me an overall omnibus test comparing my compact model to my augmented model, but I also get some output with specific regression coefficients. What do those mean? I talked about this a little bit last time and tried to kind of illustrate that they mean specific group means and contrasts, or comparisons between group means, but I want to show you that again, and I want to show you it in a slightly different way now by plugging in values to the regression equation, the equation for our augmented model, and showing how you can solve algebraically for the regression coefficients, b sub 0, b sub 1, b sub 2, and so on. Now, in order to do this, I need to remember an important point, and that point is that in ANOVA, for the augmented model, the best prediction that we can make for someone's score on the outcome variable is going to be the average for the group that that person is in. So if I show you my data and I say, okay, here's this one person in my data set, what's your prediction for what his score is going to be on the outcome variable? If you don't know anything else about the person, the best prediction you can make is based on whichever group that person's in. So if I say, oh, that person's in the placebo group, your best guess for her level of the outcome variable will be the average for people in the placebo dose group. Now, this is really useful because it allows us to solve for the regression coefficients in our model by just doing some relatively simple algebra. And here's how this works. Let's begin with our placebo dose group. This is the group that gets 0, 0 as the codes for the dummy-coded variables. So here's our regression equation. There are two predictor variables. Those are the two dummy-coded variables, and so we have regression coefficients for each of those variables and then a regression coefficient for our intercept. Let's substitute in 0, 0 for x sub 1 and x sub 2 and solve the equation. Well, we have the predicted value for people in the placebo dose group is going to be equal to b sub 0. Now we know that the predicted value for people in a given group is the mean for that group. So this tells us that b sub 0 is the mean for the placebo dose group. And if you think back to the last lecture, you noticed that, or I showed you that, but here's kind of the same thing expressed algebraically. I've solved for b sub 0 and shown myself that what b sub 0 is using the dummy coding scheme that I've chosen is it's going to be the mean for the placebo dose group. I can use this same approach to solve for the other groups. So the high dose group is the group of people who have code 1, 0 for x sub 1 and x sub 2. I substitute in those two values here, and now I'm talking about the high dose group, so my predicted value for the high dose group is going to be equal to b sub 0 plus b sub 1, because of course the x sub 2 is 0. So the predicted value for the high dose group is going to be the average for the high dose group, and the predicted value for the placebo group, well, that's b sub 0. I've already solved for that, and just by rearranging the algebra here, or rearranging the equation here, I can show that b sub 1 is the difference, or the contrast, between the average for the high dose group and the average for the placebo dose group. So just to spell that out, b sub 1 is the difference, or the contrast, between the prediction for the placebo group and the high dose group. It's the difference between these two means. And if you think back to the last lecture, of course I showed you that, but again I'm just trying to kind of express it or show it algebraically in this lecture. Now we've got one more group, that's the low dose group. They're the people who had the codes 0, 1 in my coding scheme. So here's my equation again. Substitute in values for 0 and 1 for x sub 1 and x sub 2 respectively. Going to do a little solving here. I already know what b sub 0 is. And so again, rearranging things a bit, I can see the b sub 0 is that contrast, or that difference, between the low dose group and the placebo dose. So once again, b sub 2 is the contrast, or the comparison, or the difference between the average for the low dose group and the placebo dose group. Just to put this all together, here's my equation again, and now looking at it, I can see that I know, based on looking at B sub 0, B sub 1, and B sub 2, I know the control group mean, and I know these two contrasts, or these two differences. Now these differences work out the way they do just based on the way I set up the codes. Now had I set up the codes differently, for instance, had the high dose group been 0, 1 and the low dose group been 1, 0, the codes would have worked out differently because of the math, but otherwise, hopefully this is fairly basic and fairly obvious to you. And just as a quick reminder, in dummy coding, it makes sense that the group to assign the 00 codes, or 000, however many dummy code variables you have, to assign the 00 codes to the group that makes the most sense as the comparison. In the case of a drug study, as I said last time, the group that's the placebo dose group or the no dose group makes the most sense. If this was like a study of psychotherapy, maybe the people who are on the wait list group who haven't been assigned to therapy, you'd give them that code. Or if this was some sort of experimental laboratory study, the group that got no manipulation or stimulation or whatever, you'd give them that code because they're the most sense as the comparison. You don't have to do it that way, it just seems like it makes the most sense. And again, I know I used this image last time, but I'll use it again. It's just a nice reminder and kind of pictographic representation of the fact that B sub 1 and B sub 2 represent quite literally these differences or these contrasts between means from different groups. So the important point here is that when you use dummy-coded variables to run an ANOVA as a regression, the regression coefficients for those variables have meaning. The meanings are, well, they're either going to be group means or contrast between group means. And so you have some flexibility here. You can create a coding scheme that gives you the contrasts you want. I should also note that dummy coding is not the only way to represent a categorical predictor variable in a regression. In fact, there are other options, one of which I'll get to a little bit later in this very lecture, to again give you some flexibility to get the information that you want. That's really the key for so much of this stuff, is do the test you want, make the comparison you want, get the information that you want. Moving on, let's consider some different ways that we can do ANOVAs. Now last time I gave the example of doing ANOVA in Excel, and here I kind of ran ANOVA as a regression analysis. I used those dummy-coded variables as predictor variables in a multiple regression, and I got this nice output here. This is using the data analysis toolkit, and so I get some tables all set up for me with the familiar regression statistics ANOVA table and regression coefficients table here. I also mentioned that I could use the data analysis toolpack to run ANOVA as a more traditional ANOVA analysis, and that's also pretty easy to do in Excel. The only trick being that I have to rearrange the data into the format that you can see in kind of the top left of this screen capture here. You get basically the same results, although you get less information. You don't have any regression coefficients because it's not a regression analysis, so we don't right away know a lot about the different contrasts that we might be interested in. What I'd like to do now is run through some of those same analyses in SPSS, and if you're enrolled in my class, you can do this on your own computer, or if you have access to SPSS, you can do it on your computer at home, or indeed wherever you are. The first thing I want to do is run my analysis as a regression. So I'm using that same data, and I've got my dummy-coded variables already set up, and I'm going to analyze regression linear, opening up the linear regression module, and my my outcome variable or dependent variable is libido. That's the outcome variable for this analysis. My predictor variables are going to be those dummy-coded variables. Now notice here that I'm not using the categorical predictor variable in my analysis. Instead, I'm substituting in those dummy-coded variables in one block. So this is not a hierarchical multiple regression. Now obviously you can ask for different options and regression diagnostics. I'm largely going to skip those for the time being and just quickly move on to the output. The output looks a little bit like this. You can see the familiar model summary, you can see the ANOVA table, and you can see the coefficients. And the important thing, or at least an important thing to focus on here, is that as we saw before, the model is significant, meaning the comparison between the compact model and the augmented model well, is statistically significant. The p-value is less than 0.05, and we can say that we can reject the null hypothesis. We can say that a model which includes information about the categorical predictor variable is associated or explains more of the variance in the outcome variable than a model which does not, a compact model. Let's go ahead and do the same analysis, except this time we're going to run the ANOVA in a more traditional way using the ANOVA module in SPSS. So here it's analyze, compare means, one-way ANOVA. One way just means that we have one and only one categorical predictor variable. Open up the little dialog box for one-way ANOVA. The dependent list is going to be where we put our dependent or outcome variable, that's libido. And instead of using those dummy-coded variables now, I'm going to put my categorical predictor variable on the factor, or in the factor box. Recall that factor is a term that is just used to refer to variables, especially predictor variables, historically in the world of ANOVA. Now again, you have some options here, not as many as you have in the regression module. You can play around with them if you want, but I'm just going to hit OK and proceed to the output. The output looks a little bit like this, and it's very simple. If you didn't ask for any additional options, you just get one element, one table, an ANOVA table. And although the naming conventions of this ANOVA table are a little bit different than the ANOVA table associated with the regression output, essentially the information is the same. The sums of squares, degrees of freedom, mean squares, f, and significance level are all exactly the same. So same data analyzed in a somewhat different way, we get the same output, albeit somewhat less information than if we did the analysis in the regression module. Let's do this a third way. Let's use the general linear model module in SPSS. And in this unit and in the next unit, we'll be using this module a lot. So now's a good time to introduce it. Go to Analyze, General Linear Model, Univariate, and our dependent variable or output variable, or outcome variable, will be libido. Here we're going to use our categorical predictor variable. We don't need to use those dummy-coded variables, and we're going to put that categorical predictor variable in the box for fixed factors. You can click on a lot of different options here. The only one I'm going to do is if I click on the options box and select parameter estimates here, you can see that I've checked that. I'm going to hit continue and hit OK and move on to my output. Now the output for general linear model can be quite a bit more complicated than some of the output that we've previously seen, but here I'm just highlighting some important pieces. First, we have a table called test of between subjects effects, and if you see here there's a line called corrected model, which contains the same sum of squares and mean squares and f statistic and p-value that we saw on the ANOVA tables in our previous analyses. So essentially we are getting the same analysis, although it's presented somewhat differently, and I'll talk through in a future lecture the other elements of this between subjects effects table. Also notice that we have a table for parameter estimates. That's at least if you asked for one, and this looks a little bit like the table for regression coefficients that we saw in our output for our regression analysis. So for instance, here is that table of regression coefficients from our regression output, and here is the table of parameter estimates for our GLM output. And again, it's not exactly the same, but it sort of looks a little bit familiar. That said, these coefficients are different. At least some of them are different. Why is that? What does this dose equals ... dose equals 1, dose equals 2 actually even mean? What's going on here actually has to do with dummy coding and the way that our categorical predictor variable dose is coded in either the regression analysis or in the GLM analysis. So here's the dummy coding that we used when we set up our dummy code variables for for our analysis and regression. And we set it up this way because we wanted to use the placebo dose group as our reference or our baseline or as our comparison. So we gave that group the 0, 0 codes, as you of course remember. And so here's that output that we've seen before, and because of the nature of the coding, our intercept, or the constant, is the mean for the placebo group. B sub 1 is the difference between the placebo group and the high dose group, and B sub 2 is the difference between the placebo dose group and the low dose group. Here's what happened in the GLM analysis. When we asked SPSS to treat dose as a fixed factor, it used dummy coding, but it used dummy coding in this way. It put the 0, 0 code for the highest level of the categorical predictor variable. In this case, that happened to be the high dose group. And then it proceeded from the lowest group to the highest group by assigning 1, 0, and then 0, 1. Now this isn't wrong. It just means that the high dose group now serves as the reference because it's the group that had the 0, 0 code. And we can see that if we look at these parameter estimates. The intercept is now the mean for the high dose group. And what SPSS calls dose equals 1 is the difference between the placebo dose group and the high dose group. And what it calls dose equals 2 is the difference between the low and the high dose group. Again, this isn't incorrect, it's just a consequence of the dummy coding system that the GLM module did for us when we entered dose as a fixed factor. So the important point here is that dummy coding is just this way of handling categorical predictor variables. It's how we, or SPSS, can set up codes, and how we set up those codes matters for how we can interpret the parameter estimates or regression coefficients that we get from our analysis. And by the way, as I've mentioned already, there are other ways to set up codes for these analyses, and I'll talk about one in just a few more slides. But don't worry if this seems a little bit confusing. I know I'm throwing a lot of information at you, regression, ANOVA, codes, parameter estimates, and so on. Here's a picture of a little puppy sitting in a small bowl or something. There, that's cute. That's relaxing. Hopefully that makes you feel comfortable. Seriously though, don't worry. If this stuff seems hard, you'll get the hang of it. Just stick with it. And with that in mind, let's move on to the next part of this lecture where I talk about planned contrast. Essentially what I'm going to do here is introduce a new type of coding system, not dummy coding, but something a little bit different that allows us to get at comparisons between groups that we want to compare in our ANOVA type analysis. So here's our example again. Imagine we're a clinical pharmacologist. We're studying the effect of a drug, and what's commonly done in pharmacology research is that comparisons are done by first comparing any level of the drug dose against no drug dose. So in our case of our example, maybe the high and the low dose combined, but compared to the placebo dose group, and then comparing different levels of the drug dose. So in our example, we might, after first comparing high and low dose to placebo dose, we might then compare high dose to low dose. Now, again, this is commonly done in drug studies, and really what it does for us, or how it works in this example, is it just extends the basic idea of ANOVA. In ANOVA, what we've been doing so far is we've been breaking down variance into components. And we've been looking at systematic variation, that's variation associated with a predictor variable, which we can represent as the sum of squared error reduced, that is, the sum of squared error that's reduced when we compare the compact model to the augmented model. That's systematic variation, that's signal. We're comparing that to unsystematic variation. That's variation that's not associated with our predictor variable. And this we represent with the sum of squares error for the augmented model. The sum of squares error, the amount of error that's left over that it can't be explained by the augmented model. What's different now, or what's the addition now, is we're taking that sum of squares error that's explained by the model, sum of squares error that's reduced when we flip from the compact model to the augmented model, and we're further breaking it down into components that correspond with contrasts or comparisons that we're interested in. So in this case, we want to take that sum of squares error reduced, or sum of squares error sub m as the book notes it, and break it down into a comparison of low and high dose group compared to placebo dose group, and then low dose group compared to high dose group. Now, in one way of thinking about this, this is like taking a cake and slicing out pieces of the cake being variance. We're slicing out portions of the cake that correspond with different hypotheses we're interested in. We're slicing up those slices into successively smaller slices. Another way of thinking about this is comparing chunks of variance that make meaningful comparisons based on our hypotheses. By the way, this is just another important reason to have clear hypotheses in your research. So in this particular example, we might have one research hypothesis that goes something like, well, people who take any amount of this drug will have a higher libido, that's our outcome variable, than those who take no drug, those who get the placebo dose. And we might be doing this because we want to test or rule out an expectancy effect. It's possible that just believing you're using a drug gives you the drug effect. The placebo effect, if you will. If that was the case, then we'd expect the placebo dose group to be equal to the low and the high dose group combined. That would be our null hypothesis. Obviously, our alternate hypothesis would be that there's some difference between these two groups. Placebo dose group is not equal to low and high dose group. Now, having established that there's a difference, hopefully, between the placebo dose group and the low and high dose group combined, we might further have a hypothesis that people taking relatively more of the drug will have more of an effect than people taking relatively less. So here, our null hypothesis would be, well, no they don't. The low dose group and the high dose group are equal, but our alternate hypothesis would be that there's some difference between the two of them. Here's a picture from the text that uses the same example, except here we have 4 groups, and we could propose 3 different contrasts. The first contrast comparing levels 1, 2, 3, maybe like low, medium, and high dose to the control group, then low compared to medium and high in contrast 2, and then just medium and high compared to each other in contrast 3. Same basic idea. In our example, we only have 3 groups, and we're only going to do 2 contrasts, but it works basically the same way. In the contrast 1, we're comparing the average of the high and the low dose group to the placebo group. And in contrast 2, we're comparing the low dose group to the high dose group. And you can just see the numbers for those comparisons in the little pull-out boxes. And of course, the whole point of doing these statistical tests is to see whether these differences are statistically significant. Now, if you're paying close attention, you might be wondering, well, what about comparing the low dose group to the placebo dose group? That didn't occur in any of the previous contrasts, and it didn't occur because we didn't make any hypotheses about that difference. Again, this is one of those other reasons why it's good to have clear hypotheses. Maybe in this case we didn't really care if there was a significant difference between the placebo dose group and just the low dose group. Assuming we change our mind at some point, we could of course test this, but we'd have to test it as a post hoc test. We'd have to treat this as maybe an after the fact test, maybe do a t-test to compare the two, and by doing so we're of course adding another test to our growing family of tests, which at an extreme could be a problem for us. Anyway, given that we just have these 2 contrasts that I've outlined before, here are the codes that we could use to define these contrasts. This is contrast coding, so you'll notice it's a little bit different than dummy codes. Dummy codes could only be 0 or 1. Contrast codes are going to be 0 or positive or negative integers, or technically they could also be fractions, although I'll handle that in a supplemental lecture, or at least I'll handle that later. For the time being, let's just focus on integers. Now, in order to pick values for these integers, we're going to follow some basic guidelines. First, we're going to choose sensible weights. Those numbers, the absolute values of those numbers, those are called weights. And we're going to do so in a way that allows us to compare chunks of variance associated with different groups or combinations of groups. And we want to compare groups by assigning negative weights to one half of a comparison and positive weights to the other half of a comparison. And groups which aren't given a weight, which aren't given a weight, which are given 0, are not included in contrasts. So let's see how this works. In our first contrast, we're comparing the placebo dose group to the low and high dose group combined. So we've got these two chunks of variance. We want to compare them, so that means one chunk has to get a negative value and the other chunk has to get a positive value, but those two values need to add up to 0. They need to balance each other. So we might assign -2 to the placebo dose group and +1 to the low and high dose group respectively, because of course that sums up to 0. Now, of course, these numbers really could be any values. They could be, -200 and +100, +100, or as I noted briefly before, they could be fractions. And in a sense, it doesn't really matter. The comparison will still work. The only thing that will change is the scaling of the contrast, which we can handle and which I talk about a little bit in a supplemental lecture. But for the time being, the point to notice here is that we're balancing negative and positive, and we're balancing the absolute values of these weights such that they add up to 0. Here's our second contrast. Here we're comparing just the low dose and the high dose group, so we're going to assign each of them a value of, as you can see, 1, -1 and +1, because of course that adds up to 0. Now the placebo dose group isn't in this contrast, so it just gets a value of 0 assigned to it. And of course, in contrast to -1 and +1, sum up to 0. So if we go back and look at these codes, you can see we've got, this table here calls them dummy variables. They're not really dummy codes because dummy codes can only be 0 or 1. I prefer to call them contrast codes. But in any case, you can see for contrast number 1, we've got -2 assigned to placebo people and 1 assigned to low and high dose people. In contrast 2, we've got 0 assigned to placebo, -1 assigned to low dose, and +1 assigned to high dose. In each comparison, we're comparing two chunks of variance, and the negatively coded chunk is compared to the positively coded chunk, and within each contrast, the weights sum up to 0, just like I described before. Now, we're also comparing unique chunks of variance, and what that means is that a chunk of variance that's pulled out in one contrast isn't included in another contrast. Now, what I mean by that is, in the first contrast, we're comparing placebo to low and high dose. So in a sense, we're kind of isolating placebo and comparing it to those other two groups. We don't want to then recycle placebo in our second contrast, like compare placebo to just the high dose group in our second contrast. We could do that, but those wouldn't be then unique comparisons. They wouldn't be orthogonal comparisons. And there's a way you can kind of check the math on this really quickly. If you multiply across the columns for your contrast codes and then sum down the products of those multiplications, and those sum up to 0, then you've got unique orthogonal contrasts. If that's hard to visualize, I actually find it easier just to look at the way the coding appears in a spreadsheet or in a data frame like this. And you can see here for the placebo dose group, we're pulling out the placebo dose group in contrast 1, and then we're not including it in contrast number 2. In contrast number 2, we're pulling out the low dose group and comparing it to the high dose group. Now, I said these contrasts are orthogonal, and orthogonality is kind of a complicated concept, and I will talk about it in a supplemental lecture, but for the time being, let's just think about it this way. Orthogonal contrasts are contrasts that are set up such that once a chunk of variance is pulled out, as I've said before, in one contrast, it isn't recycled in a subsequent contrast. And if you want to think back to that cake metaphor, it's like once you've sliced out a piece of cake, you don't then squish it back into the cake and then slice it out in some other combination later on. Once you've sliced out a piece of cake that corresponds to the placebo dose group and compared it to some other slice of cake, then you set placebo dose group off to the side and you take that other slice of cake and you slice it up, and then maybe you set part of that off to the side and take the remaining piece and slice it up, and so on and so on. Now, people like orthogonal contrasts for a number of reasons, and again, I'll talk about this in a supplemental lecture, but for the time being, one of the reasons we like it, or we like them, is they help us to manage family-wise error rate because they limit the number of tests we can do. There's a limit on the number of orthogonal contrasts you can set up for any number, for a given number of groups or a given number of levels of a predictor variable. And if you commit yourself to doing only orthogonal contrasts, you're kind of committing to a relatively smaller number, total number of tests in that family than you would be if you allowed yourself to do non-orthogonal contrasts, which are perfectly acceptable. They're just different. And again, I'll talk about that a little bit later on. So anyway, using all this, let's run some basic analyses. If you're in my class, I have a data set called Viagra number 3. That's just the same data, except it's set up with some different dummy and contrast codes for you to play around with. So the first thing I want you to do is just run the ANOVA as a regression using the regression module and using those dummy codes. So you may have already done this, but if you haven't, just go ahead and do it now. Here's that regression output using our dummy codes. And again, what's nice about using regression as our kind of workspace in SPSS is we can interpret those regression coefficients as means and comparisons between means, and we get things like t-tests and p-values and confidence intervals, which can be useful, assuming that we are interested in comparing, for instance, placebo dose to high dose, placebo dose to low dose. By the way, notice here that dummy codes are always non-orthogonal. You can see that placebo dose group is sort of recycled across these two contrasts. Placebo compared to high, placebo compared to low. Now, to be clear, that's not bad. It's just non-orthogonal. And again, I'll talk about that a little bit more in a supplemental lecture. Now let's do the same analysis, except instead of using our dummy codes, let's use some orthogonal contrast codes that I set up. And these correspond to the ones that I've described previously in this lecture. So if you can't see my, behind the dialog box in my image here, you could in SPSS or in Excel just enter in those contrast codes that I described earlier. So here's our analyses, the ANOVA table when we use the dummy codes from before. And here's the analyses, the ANOVA table, using our contrast codes. And of course you can see they're exactly the same. Because we're explaining the same outcome variable with the same predictor variable, we're just coding that predictor variable differently when we use a pair of dummy codes and when we use a pair of contrast codes. And here are the coefficients when we use the dummy codes. And here are the coefficients when we use the contrast codes. And of course these are different because they correspond to, or they refer to, different comparisons. And again, this depends entirely on what you are interested in. If you want to compare each dose to the placebo dose, then clearly the dummy codes are the right way to go. If you like this approach of doing placebo and low and high versus placebo, then low versus high, then these contrast codes make a lot more sense for you. The important point here is that learning how to use codes, dummy codes, contrast codes, and so on, gives you some flexibility. It allows you to use the regression module of SPSS or regression procedures in Excel to get comparisons that you want or that you care about for your research. And that's really valuable. That's super useful. And I'll talk about that a lot in future lectures. But we've kind of run out of time, or at least I've run out of time. I'm a bit tired, to be honest, at this point. Here's a preview for what we'll do next time. We'll talk a little bit more about non-orthogonal contrast. And to be clear, these are not bad to do. They're just a different option you have. It's worth understanding how they work. I'll also talk a little bit about post hoc tests and, as you can see, some other cool stuff. So anyway, that's all for today, or all for this time. Thank you so much for your attention. I really do appreciate it. Hopefully you learned something. If you're in my class and you want to ask me a question, by all means do. If you're on YouTube just watching these videos, post a comment. I try and look for those. If I see them, I'll try to respond to them. Thanks so much. Bye-bye.